we are now looking at Notes U, Part 2, and we are going to get into algebraically finding inverses. This is the fun stuff, in my opinion. Here's the steps for writing the formula for the inverse of f of x. Very first thing you're going to do is you're going to write y in place of f of x. We know those two things mean the same thing, but it's going to help me to have just a plain old y. We're going to flip-flop, we're going to swap our x and our y. Technically now this is the inverse of f of x, but we need to resolve this in step 3 for y, and then the very last step we are going to write our function notation as the inverse of f of x. Sorry, that didn't make it into the superscript in the PowerPoint font. All right, so let's see this in action. Here comes the fun stuff. All right, we want to find the inverse of h of x equals the cube root of x minus 4. So first up, we need to replace that h of x with a y. The generic instruction said to replace f of x with y. H of x is the same thing. So step 1, we are going to have y equals the cube root of x minus 4. Now in step 2, I'm going to switch my x and my y. So now I'm going to end up with x equals the cube root of y minus 4. All right, now in step 3, I need to resolve this equation for y. Excuse me. How do I undo a cube root? I cube it. So I'm going to cube both sides here. Now, on the right-hand side of my equation, my cube and my cube root are going to undo each other, and I'm going to be left with x cubed equals y minus 4. Remember, my goal here is to get that y back by itself. I'm really close. I need to add this 4 over to the other side, so I'm going to get x cubed plus 4 equals y. My very last step is to replace that y using my proper function inverse notation. So I'm going to have the inverse of h of x equals x cubed plus 4. There we go. Not so bad. Kind of fun, right? Okay, now we want to find the inverse of, whoops, I skipped one. The inverse of g of x equals 2x cubed minus 5. First up, we got to replace that g of x with a y. So we get y equals 2x cubed minus 5. Now we swap the x and y. X equals 2y cubed minus 5. I need to resolve this for y now. Very first thing I need to do is I need to add that 5 over to the left-hand side. So I'm going to get x plus 5 equals 2y cubed. Now the 2 is attached to the y cubed with multiplication. How do I undo multiplication? You got it, division. So I need to divide by 2. I'm going to have x plus 5 divided by 2 equals y cubed. How do I undo a cube? Cube root. So I'm going to have the cube root of x plus 5 over 2 equals y. Very last step is to use my fancy pants function notation for my inverse. So I'm going to have the inverse of g of x equals the cube root of x plus 5 over 2. Might not look pretty, but it's beautiful to me. You're good to go. All right, next one gives us a fraction, a rational expression. We want to find the inverse of g of x equals x minus 3 over x plus 2. Replace that g of x with a y. We're going to flip-flop the x and the y. So we're going to have x equals y minus 3 over y plus 2. Notice that my original function had x's in 2 different places. So when I switch my x and y, I'm now going to have y in two different places. And that's totally fine. Just realize that's what's happening, and we're going to have to address that. Now, anytime I have a fraction, if I want to get rid of my fraction, I can multiply by the denominator. So I need to have x times y plus 2 equals y minus 3 over y plus 2 times y plus 2. Because whatever I do on one side, I have to do to the other. Now, the beauty of that is I no longer have a fraction on the right-hand side now. I have x times y plus 2 equals y minus 3. Any thoughts on what I should do next? Yeah, let's distribute that x. We're going to have xy plus 2x equals y minus 3. Now, we got to keep our eye on the prize. Remember, we are trying to resolve for y. That means I need to get all my y's onto one side of the equation and everything else to the other side. Let's move all my y's to the left-hand side. So I'm going to move this y from the right to the left. And I'm going to get xy minus y. I'm going to move that 2x from the left to the right and end up with negative 2x minus 3. It's also okay to write negative 3 minus 2x. Same thing. Notice both my terms on the left have something in common. What is it? Yeah, they both got a y. So I'm going to factor that out front, and I'm going to have y times x minus 1 equals negative 2x minus 3. Very last step. How are my y and my x minus 1 connected? Multiplication. How do I undo multiplication? Division. So I need to divide both sides by this quantity x minus 1. And I am going to get my final result of y equals negative 2x minus 3 over x minus 1. Very, very, very last step, we got to use our proper notation. We are now going to write that the inverse of g of x equals negative 2x minus 3 over x minus 1. This is a good one to put a star in on your notes, maybe fold over the corner of the page. This is something that likes to come up on the next test as well as the final exam. So if we kind of go back and recap on this one, the key here is that we have to get all the y's over to the left-hand side of the equation, factor out that common factor of y, and then divide. Okay, now here's a really cool thing about inverses. We're going to tie this back to our function composition. If f and g are inverses of one another, then f of g of x, so when I plug g of x into f of x, I'm going to find out that it just equals x. And g of f of x, so if I plug f of x into g of x, it's also going to just equal x. It's pretty cool. So let's see this in action. I've got f of x equals 2x plus 3, and I have g of x equals x minus 3 over 2. And we want to show that they are inverses of one another. The way that we are going to show this is using that really cool fact that I just taught you guys, that f of g of x equals x and g of f of x equals x. So we're going to find both compositions, and as long as they both equal x, then we have confirmed that these two functions are inverses of one another. All right, let's start with f of g of x. So f of g of x, remember this means I'm going to plug g of x into f of x. So I'm going to have 2 times x minus 3 over 2, use those parentheses, plus 3. Here's where the magic happens. I now have x minus 3 plus 3, but that is really just x. Voila. Pretty cool. We also have to show this in the other direction though. So it has to be true in both directions of composition. So now we need to show g of f of x. Now I'm going to take f of x and plug it into g of x. So I'm going to end up with 2x plus 3 minus 3 over 2. Now, in this case, always smart to use parentheses when you plug in, but they're not doing anything here. So that 3 minus 3, peace out. We now have 2x over x. Nope, 2x over 2. And what's going to happen with those 2's? They're also going to reduce, and we are just left with x. How cool. So we have just showed that because f of g of x equals x and g of f of x equals x, these two functions are inverses of one another. I want to show this to you also from a visual standpoint, okay? If we check out these two functions as graphs, so what do we have? F of x equals 2x plus 3, and we had g of x equals x minus 3 over 2. I'm going to rewrite that as 1/2 x minus 3/2. So remember that 2 belongs to both pieces in the numerator. That just gets me into that y equals mx plus b form. All right, let's check out f of x. Let's do this one in blue. We are graphing 2x plus 3. We have a y-intercept of 3, and we have a slope of 2, so we're going to go up 2 over 1. I'm going to give myself a couple extra points so that I can get myself a nice straight line, hopefully. There we go. Okay, and now let's do the same thing with g of x. G of x, we have a y-intercept of -3/2, so -1.5, and we have a slope of 1/2, so we're going to go up 1 over 2. Up 1 over 2. We can also go down 1, left 2. Let's get that nice straight line. And we now have the graph of g of x as well. Okay. You're going to find that anytime you graph two functions that are inverses of one another, that they are always going to be symmetric across this red line that I just drew. That red line is the line y equals x. It has a y-intercept of 0, so it goes to the origin. It has a slope of 1, so you're going to find that it's up 1 over 1. Every single function that has an inverse, if you graph both of them on the same coordinate grid, you are going to find that they are symmetric to y equals x. So previously, we looked at some symmetry like x-axis symmetry, y-axis symmetry, origin symmetry. This is another way that symmetry shows up in graphs and their inverses. Now, one last piece of information to think about here. Remember that when we find inverses of functions, we are switching our x's and our y's. Because we're switching our x's and our y's, the domain of a one-to-one function, the x values of our one-to-one function, are going to become the range of the inverse. And vice versa, the range of a one-to-one function is going to become the domain of its inverse. And that's all because we're switching our x's and our y's. Okay, last problem here, we want to consider f of x equals x squared. Now, we previously looked at a parabola, a quadratic function, and determined that it was not one-to-one because as is, it would not pass the horizontal line test. So we knew that right away it was not one-to-one. Okay, but let's think about what would happen if we only looked at part of this graph. Okay, what if we only looked at when x was greater than 0? So we're only looking at this right-hand side of my parabola. If I were to only look at that right-hand side of my parabola, so I limited my domain from 0 to infinity, so this is my original function where I'm just looking at that right-hand side, my range would be also 0 to infinity. Okay. My inverse, when I switch my x's and my y's, would look like this now. Okay. This means that the domain of my inverse function, I know, is the range of my function. So this domain matches up with the previous range. And I know that my range is going to match up with my domain. Now, it just so happens in this example that they both are 0 to infinity, but realize that the domain of my function becomes the range of my inverse. The range of my function becomes the domain of my inverse. And just like we discussed before, remember that this graph is symmetric around that line y equals x. All right, that's it for inverses. I hope you enjoyed it. Let me know if you have questions.